Good morning, kids, and welcome to the world of science.
Hello children, today we have a ball of mass 3m and a ball of mass m. What we're going to do is release them simultaneously in shown position with air resistance being negligible, and after a certain time they will be in this position. As soon as the mass 3m ball hits the ground, it will be traveling upward with a speed v sub b. Now this ball of mass m will be traveling downward with that same speed. This is after they fall the equal distance h. Some of the most important physics principles involved in the problem today are conservation of momentum, conservation of mechanical energy. Alright, now this theory is that without any external forces acting on a system, both mechanical energy and momentum will be conserved throughout the problem. These are critical to understanding and solving this problem.
Hi, kids. I'm Scientist Jamie, and today we're going to try this experiment where we drop this big ball, mass 3m, and this tiny ball, mass m, onto each other. My friend Tyler explained what we're doing before, but today we're actually going to look at it. So, since we are doing the experiment, make sure to wear your safety goggles at all times. Now, when this ball hits the ground, this ball is going to be just a little bit above it, and it's going to be going down at the same speed this ball is going up. Hopefully, this ball, the tiny one, is going to fly off into nowhere. Let's see if it works. Oh! It works!
Hi, I'm physicist Ben, and this is physicist Uncle Sam, and we'll be showing you how to solve the problems to the question today. Me and physicist Mr. Popper here are going to show you how to do the first part. For the first part, they asked you to solve for VB in terms of m, h, and other fundamental constants. To solve part A for v sub b, we're going to start with the equation v sub b squared is equal to the initial velocity squared plus 2ad. Since the balls were dropped from rest, v sub 0 is equal to 0, so we can get rid of that. Also, the acceleration is due to gravity, for that is the only force acting on the system. And since the distance was already given to us as h, we will include that instead of using d. Now, we are left with v sub b squared is equal to 2gh. Simply square root each side, and you'll finally get your answer of v sub b is equal to the square root 2gh. For part B of the problem, they want us to relate VB, VS, and VL all in one equation. Me and the dogs here will show you how to do that. For part B, we're going to start with the fact that momentum is conserved. Because of this, we can set the momentum before the collision equal to the momentum after the collision. With that, we have that set up here, and just some simple algebra will get you to the final solution of 2v sub b is equal to 3v sub l plus v sub s. Daz here will show you how to do part C. Look at him getting some hang time, square root of 2h over g. Alright, now for part C, they want us to solve for v sub s using our relationship from part B. And we're going to be solving for v sub s in terms of v sub b. Also, in part C, they tell us that v sub l is equal to 0. So we start with our initial equation of 2v sub b is equal to 3v sub l plus v sub s. We plug in v sub l is equal to 0, and you'll finally get v sub s is equal to 2v sub b. part D here, me and my buddy, the Green Lantern, will figure out if the collision is elastic. If the collision is elastic, then kinetic energy is conserved. First, we set the kinetic energy before the collision equal to the kinetic energy after the collision. Then we make a key substitution of V sub B is equal to V sub S over 2. Collect like terms, and kinetic energy before is equal to kinetic energy after the collision. Because of this, we can say the collision is elastic. Remember physicist Uncle Sam? Well, he's back for part E. He's going to help you figure out how high the small ball, mass m, rises above its lowest position in terms of h, the original constant. For part E, we will start with setting the kinetic energy equal to the potential energy, for at the ball's highest point, it will have all potential energy and no kinetic energy. We can do this because energy is conserved. Then, we replace V sub S with an equal value, 2V sub B. Next, we refer to part A and replace V sub B with the square root of 2GH. Simplify this equation and the result will be the height, y, is equal to 4h.
Scientist Leo here, on the scene. I'm going to talk to you about how conservation momentum can help you in the real world. You may see a game of billiards right here, but what I see is a laboratory full of geometric and physical equations, and we're going to go in depth on how physics can help you at a game of pool. Now you see 15 balls right here in perfect alignment. See what happens when I introduce a vector of force from this cue ball and how it reacts with all the other balls who transfer its momentum. Bullseye. Good. Now this is an in-depth synopsis on what's happening right now. I'm going to hit one ball, give it some kinetic energy, send it in motion. It's going to collide with that number 11 ball right there. It's going to be sort of elastic, as this will still have a little bit of motion afterward, just due to some drag. But most of its kinetic energy and momentum will be transferred into that ball, shooting it off into space with the same angle and near same magnitude. The experiment we did before, it was nearly completely elastic. In that situation, all this momentum would be transferred to the collision point and sending this one off, leaving this one stationary and having no momentum. But combined, the mass times velocity on this would be the same as the before mass times velocity on this when the collision occurred. And that, in a perfect scenario, would stay still. Next time you play billiards, remember both your chalk and your equation sheet.